Hello, this is Math 2115 coming to you from the College of DuPage during the fall of 2020. And this lecture is the continuation of the logic of quantified statements. When last we left off, we were working on this problem. I hope you finished it, but maybe you didn't. And so I will give you a little bit more time now. You know what to do. Let's see how you did. So this statement, for every x, an element of the real numbers, x squared is bigger than or equal to 1, can be translated in a number of ways. Every real number has a non-negative square. All real numbers have non-negative squares. Any real number has a non-negative square, or the square of each real number is non-negative. This one, which says for every x, an element of r, x squared does not equal 2 minus 1, could be translated a number of ways. All real numbers have squares that do not equal minus 1, or no real number have squares equal to minus 1. The words none are and no are equivalent to the words all are not. The last one, there exists at m an element of the positive integer such that m squared is equal to m, can be translated in a number of ways. There is a positive integer whose square is equal to itself, or we can find at least one positive integer equal to its own square, or some positive integers equals its own square, or some positive integers equal their own squares. There's another example dealing with trailing quantifiers. We're to rewrite the following statement so that the quantifier trails the rest of the sentence. For any integer n, 2 times n is even, and there exists at least one number x such that x squared is less than or equal to 1. You know what to do. Let's see how you did. So, some ways you can write it is 2n is even for every integer n. Or, the second one has a couple of ways listed. X squared is less than or equal to 0 for some real number x. Or, x squared is less than or equal to 0 for at least one real number x. And in fact, that number is 0. Here's another example where we're to rewrite each of the following statements formally using quantifiers and variables. So we have all triangles have 3 sides, no dogs have wings, and some programs are structured. You know what to do. Let's see how you did. For every triangle T, T has 3 sides, or for every T, an element of T, T has 3 sides. Here you're saying T is the set of all triangles. No dogs have wings mean for every dog D, D does not have wings. Or for every D, an element of D, D does not have wings, where capital D is the set of all dogs. And the last one would be there exists a program P such that P is structured, or perhaps there exists a P, an element of P, such that P is structured, where P, capital P, is a set of all programs. Here's another example. We're writing something that we're given formally. We're writing it informally. What does it mean? So, for every x, an element of r, if x is bigger than 2, then x squared is bigger than 4. You know what to do. Let's see how you did. If a real number is greater than 2, then its square is greater than 4, or whenever a real number is greater than 2, its square is greater than 4, or the square of any real number greater than 2 is greater than 4, or the squares of all real numbers greater than 2 are greater than 4. Here's another example. What we're trying to do is rewrite all of these 3 sentences in this form where we're doing it formally. So this is for every blank, if blank, then blank. You know what to do. Let's see how you did. So the first one you would write, for every real number x, if x is an integer, then x is a rational number, or purely in symbols, for every x, an element of R, if x is an element of Z, then x is an element of Q. And here we're using R, Z, and Q to stand for the sets of numbers that we've talked about. For B, for every x, if x is a byte, a computer byte, then it has 8 bits. And C is, for every x, if x is a fire truck, then x is not green. Here's another example. We're to rewrite the following statement, which is all squares are rectangles, in two forms. For every x, if blank, then blank, and for every blank, x blank. You know what to do. Let's see how you did. And so a way to write it would be, for every x, if x is a square, then x is a rectangle, or for every square x, comma, x is a rectangle. Similarly, a statement of the form, there exists x such that p of x and q of x can be written as, there exists x, an element of D, such that q of x, where D is the set of all x for which p of x is true. Here's a definition of prime numbers. I don't know that we've taught about that. And then an example for you to fill in the blanks again. So here we go. A prime number is an integer greater than 1 whose only positive integer factors are itself and 1. So consider the statement. That's the definition. Now consider the statement. There is an integer that is both prime and even. Let prime of n be the statement, n is prime, and even of n be n is even. Use the notation involving these definitions to rewrite the statement in the following forms. You're filling in these blanks. You know what to do. Let's see how you did. So you could write, there exists an n such that prime of n and even of n. And for part B, there are two possible answers listed. There exists a prime number n such that even of n, or there exists an even number such that prime of n. It is prime. Now, if we consider these two statements, for every integer x, x squared is bigger than 0, and there exists a real number x such that x cubed equals 8, statements 1 and 2 both call the variable x. But the x in statement 1 serves a different function from the x in statement 2. We say that the variable x is bound by the quantifier that controls it. So up here, it's a for every, and down here it's an exist. And, so that's the bound, and that its scope begins when the quantifier introduces it and ends at the end of the quantified statement. The way variables are used in mathematics is similar to the way they are used in computer programming. A variable in a computer program also serves as a placeholder in the sense that it creates a location in computer memory, either actual or virtual, into which its values can be placed. In addition, the way it can be bound in a program is similar to the way that a mathematics variable can be bound in the statement. For example, consider the following two examples in Python. So this is the Python programming language. Here is a program 1 and here is a program 2. Now you see over here the variable of interest is x, and over here the variable of interest is s. But you see it only has the definition while we're doing this. The output for both programs is it prints hi and then bye. But in each case the variable x or s is local to the function where it is defined. These are function definitions. Here you define f, here you define f. And here you define g, here you define g, but then you close off. That finishes the definition. So the local variable is bound by the function that defines it, and its scope is restricted to that function. Outside of that function definition, the variable name can be used for any other purpose. That is why the functions f and g are allowed to use the same name for the variable in their definitions, and why f and g define the same functions in both programs. Some more notation and an example. Let P of x and Q of x be predicates, and suppose the common domain is x is an element of D. If we write this, now notice that this is not just an arrow, it's a double arrow. So this notation means that every element in the truth set of P of x is also in the truth set of Q of x. So for every x, P of x implies Q of x. The notation P of x with a double arrow, notice that these are double arrows, but they got two lines in the middle, means that P of x and Q of x has identical truth sets, or equivalently, for every x, P of x is logically equivalent to Q of x. So here is an example where you're supposed to suppose that the domain of the variable n is the positive integers. Then you're to use these new symbols to indicate the true relationships between what we're calling up here Q of n, R of n, and S of n. You know what to do. Let's see how you did. So what you should have ended up with is that R of n implies Q of n, because if n is a factor of 4, then n also divides into 8. It's n is a factor of 8. Similarly, we have if n is a factor of 4, that's logically equivalent here, so we will write it if and only if for these two. And last but not least, we will have that S of n implies Q of n. These have the same truth values. If something n is less than 5 and not equal to 3, then it has the same truth value as this. If n is less than 5 and n does not equal 3, then n is a factor of 8. Another example talks about a program that's called Tarski's World, and this is a logic training program. It provides pictures of blocks of various sizes and shapes and colors, and they're located on a grid. You can see a picture here of such a screen. So this is a picture of an arrangement of objects in a two-dimensional Tarski world. The configuration can be described using logical operators for the two-dimensional version. Notation such as triangle of x means x is a triangle. B of y means y is blue. And right of xy means x is to the right of y, but possibly in a different row. And individual objects can be given names such as A, B, and C. So what you're supposed to do is use this logical configuration. This is your world, this is your universe, to determine the truth or falsity of each of the following statements. The domain for all variables is a set of objects in the world that's shown in this picture. So you have these 4 statements that you're to determine whether they are true or false. You know what to do. Let's see how you did. Statement A is true because every triangle in the picture is blue. Statement B is false because we have a counterexample that E here is blue and E is not a triangle. C is true because E and H are both squares and D is to their right. So there exists a y such that the square of y is to the right of dy. And the last statement is false because all squares are either blue or black. There are none that are gray. We'll continue this in 6.2.